Welcome to this explainer. Okay, if you look around you right now, pretty much everything you rely on, from the lights overhead to the device you're literally using to watch this, depends on a fundamental physics principle that honestly feels a little bit like magic. Today, we're unpacking this incredible, invisible force that powers our modern world. We are taking electromagnetic induction from mystery to mastery. Okay, let's dive right into this. We've known for a long time that a current-carrying wire produces a magnetic field, right? That's the absolute basics of electromagnetism. Electricity creates magnetism. But our central mystery for today completely flips that script. We're asking, can magnetism produce electricity? Think about it. How do we generate continuous, massive amounts of power for entire cities without relying on giant chemical batteries? Well, the answer lies in the really dynamic relationship between conductors and magnets. Here's our roadmap for today. We're going to cover 1. Magnetism creating electricity. 2. Understanding magnetic flux. 3. Faraday's law of induction. 4. Finding direction with Fleming's rule. 5. Lenz's law and opposition. And finally, 6. Powering the real world. Section 1. Magnetism creating electricity. Unlocking the invisible force. So, to truly appreciate this, we have to travel back nearly 200 years to look at the historical context of our physics mystery. In the 1820s, the scientific world was absolutely buzzing with the discovery that electricity could produce a magnetic field. But it wasn't until 1831 that a monumental breakthrough happened. British scientist Michael Faraday and independently American scientist Joseph Henry figured out that the exact reverse was true. They proved that you could produce electricity from magnetism. It was a massive revelation that would literally change the trajectory of human technology forever. Which brings us to our foundational definition, electromagnetic induction. This is the process of producing an induced voltage, which we often call an electromotive force, or EMF, and an electric current across a conductor when it's placed inside a varying magnetic field. Now, the absolute secret ingredients here are relative motion and changing fields. A stationary setup? Yeah, that won't do it. You need dynamic change to spark the induction. Let's actually visualize this with a simple experiment. Imagine a horseshoe magnet and a straight wire hooked up to a galvanometer. That's just a device that detects electrical current. If you hold that wire completely still, right between the north and south poles of the magnet, nothing happens at all. Zero change means zero current. But if you rapidly move that wire up and down, cutting right through those magnetic field lines, the galvanometer needle jumps. By continuously moving the wire, you're directly converting your physical, mechanical energy into electrical energy, producing a continuous alternating current, or AC. Let's move to Section 2, Understanding Magnetic Flux, Measuring the Magnetic Flow. So before we can actually calculate the electricity we generate, we have to measure the magnetic flow itself. We call this magnetic flux, and it's represented by the Greek letter phi. It's basically the total amount of magnetic field passing through a very specific area. And we measure this in units called Webers. Give your brain a second to just process that. We aren't just looking at the magnet. We are looking at exactly how much of its invisible field is successfully piercing through a specific space. A really brilliant way to anchor this science in your mind is the water pipe analogy. Imagine magnetic flux as water flowing through a pipe. The water pressure? Well, that's your magnetic field strength. The actual water molecules themselves are your magnetic field lines, and the width of the pipe is the cross-sectional area of your wire loop. Just like a wider pipe lets more water flow, a larger area allows for higher magnetic flux. And crucially, this flux is completely maximized when your area is perfectly flat and perpendicular to those field lines. If you tilt it even a little, fewer lines pass through and your flux drops. Section 3, Faraday's law of induction, the math behind the magic. All right, now we're going to translate the physical motion we just discussed into a hard, fundamental mathematical rule. Faraday's law states that a voltage is induced in a circuit whenever relative motion exists between a conductor and a magnetic field. But the second half of that definition is the real key here. The magnitude, or the size, of this voltage is directly proportional to the rate of change of the flux. Let me really emphasize that. A constant, unchanging magnetic field does absolutely nothing, no matter how strong it is. Change is the absolute requirement for induction. Now, what's really interesting here is how elegantly this formula captures reality. E equals negative n times d phi over dt. Let's make this totally accessible. The E is just your induced voltage. The N is simply the number of turns in your wire coil, so more loops mean more voltage. That d phi over dt part, that's just calculus speak for the rate of change. Basically how fast you're moving that magnet or the wire. And that slightly mysterious negative sign at the front, we're going to dedicate a whole section to that in just a moment, but essentially, it represents an opposing force. Looking practically at Faraday's equation, it really just gives us an instruction manual for maximizing our power generation. If you want more electricity, you've got three distinct methods. 1. Increase the number of turns in your coil. 2. Increase the speed of the relative motion between the magnet and the coil. Or 3. Just increase the strength of the magnetic field itself. So more loops, more speed, or stronger magnets equals more power. Section 4. Finding direction. Fleming's rule. The right-hand rule for straight wires. Okay, so we know we're creating current, but we face a very practical problem. How on earth do we know which way the current will actually flow? For straight wires, we use something called Fleming's right-hand rule. Feel free to physically follow along at your desk for this one. Hold out your right hand and position your thumb, forefinger, and center finger so they're all at 90-degree angles to each other, kind of like a 3D axis. Here's the trick. Point your forefinger in the direction of the magnetic field, so think F for forefinger and field. Then, point your thumb in the direction of the wire's motion. Once you align those two, your center finger, C for current, will automatically point in the direction of the induced current flowing through the wire. It is literally a built-in compass for physics. Section 5. Lenz's law and opposition. The law of conservation of energy. Now, this is where the laws governing coils and energy conservation introduce a really fascinating and honestly somewhat counterintuitive twist. So, the crucial point is this quote by German physicist Heinrich Lenz from way back in 1834. The direction of an induced EMF is such that it will always oppose the change that is causing it. This perfectly explains that negative sign we saw earlier in Faraday's formula. The universe demands that energy is conserved. You literally can't get something for nothing. When you induce a current, that new current creates its own magnetic field, and that new field actively fights the original motion. A great way to wrap your head around this is the heavy door analogy. Imagine pushing open a massive, heavy door. The door naturally resists your push, right? It feels heavy. Similarly, when you push a magnet into a coil of wire, the induced current turns that coil into an electromagnet that actually pushes back against your magnet. It completely opposes the change. You have to physically force the magnet in, converting your mechanical energy into the electrical energy that's now flowing through the wire. Now, because of this changing flux, we actually sometimes generate currents where we really don't want them. These are called eddy currents. When a changing magnetic field hits a solid piece of metal, like the iron core of a machine, it induces these swirling, circulating currents right within the metal itself. And by Lenz's law, they act like a negative force, opposing our intended current and generating a ton of wasted heat. This is exactly why we use laminated iron cores, which are just thin strips of metal glued together in devices like transformers. It breaks up the pathway, significantly reducing those wasteful eddy currents. Section 6. Powering the real world. Translating physics into daily life. Let's connect everything we've built today back to your everyday life. And this brilliantly illustrates exactly why mastering this topic matters. These physical laws are the absolute backbone of modern technology. Electric generators and power stations use this exact principle to provide the AC power to your home. Transformers rely on changing magnetic flux to step voltages up for long-distance travel, and then step them down safely for your electronics. Even metal detectors at the airport work by sensing disruptions in changing magnetic fields. Heck, we even harness those pesky eddy currents on purpose in induction furnaces to melt down ferromagnetic metals. So, to bring our journey full circle, from the mystery of that little horseshoe magnet to the mastery of massive power plants, let's look at the basic generator cycle. Step 1. Some form of mechanical energy, whether that's wind, rushing water, or steam, physically rotates a permanent magnet inside a fixed coil of wire. Step 2. As it spins, the magnetic field lines cutting through the coil constantly alternate direction and intensity. Step 3. This continuous change in magnetic flux induces a continuous alternating current. And just like that, physical motion becomes the electricity powering the screen you are looking at right now. We've unpacked the secrets of Michael Faraday's 19th century discovery, and it's clear we rely heavily on these invisible forces of electromagnetic induction to power our modern world today. But it really leaves you wondering, if simply moving a magnet near a wire changed the entire course of human history, what undiscovered principles of physics might power our future? Thank you so much for joining me for this explainer today. Keep questioning the world around you, and I really hope this leaves you curious to explore even more physics marvels.